All right, I'd like to talk about the theory of liquid viscosity. So, we've probably all seen, at least from an introductory fluids class, the concept of Newton's law for viscosity, where the shear stress has a proportionality to the rate of shear strain. Um, what I'd really like to talk about is the molecular picture of a fluid and try to piece out a model for where this viscosity comes from. So I'm going to draw a multi-layer system here that is not, it looks kind of crystalline, but it's not really meant to be. I'll just draw a couple layers, and there's a molecule. And the key picture for a liquid is that molecules aren't really bound into an equilibrium place. They just kind of hop from site to site. Rather, they kind of slide past one another. So if I'm thinking about how all this happens, I might think about drawing a potential energy diagram where the molecule has to go, from low energy places that are far away from molecules, and it has to somehow pass over a high energy barrier to get to from site to site, basically. So the basic argument behind how a molecule moves in an environment like this is that you can think about it as a hopping event where there's a rate of hopping, let's say in the forward direction, which has sort of two parts to it. One is how rapidly a molecule is sort of bouncing back and forth, making attempts to hop over this barrier. And then the second piece is, on average, what is the probability that if I'm making an attempt to hop over this barrier, I'm going to have enough energy to do it? And so mathematically, we can express that as a frequency of oscillation. So at least at high temperature, we found that the frequency of oscillation would be something like kBt over Planck's constant. Then the second piece is that depending on how high the barrier is, there's an exponentially decreasing probability that I'm going to have enough thermal energy to get over that barrier, given the statistical probabilities associated with statistical thermodynamics. And the second part of that is to sort of understand what happens when I add stress to the equation. The idea here is that the role of stress is to actually bias transport in the forward direction. You're applying forcing that preferentially gives energy to things when they move in the forward direction, and preferentially takes away energy by doing work when a molecule tries to move in the other direction. So in other words, you can think about it as lowering the energy barrier if I'm coming from the left-hand side of this picture, or raising the energy barrier required to get over the hump if I'm trying to move in the leftward direction. We can try and apply some mathematics to that by actually using that to change our energy landscape and change our rate of hopping. The work done by the shear stress is basically the shear stress times the area over which it acts. So this is some projected top view area times the distance that the molecule would have to move. So on the upward slope of trying to go over the barrier, that would be a distance that I'll call A over 2, or the distance between two adjacent energy minima. We can be a little bit fuzzy about what that area is, because as you'll see when we're done, it basically just represents the amount of area, the top view amount of area taken up by one molecule in a plane of atoms. We can leave that a little bit fuzzy for now. Then basically all we need to do is modify the rate of hopping in the forward direction by sort of subtracting that amount of work that's being done, or subtracting from the energy barrier the amount of work being done, and then in the reverse direction adding the amount of work to make the energy barrier even higher. If I just remind you that because the forward term has the units of rate, the k's that are defined here both have units of rate. To turn those into a velocity, we need to take the rate and multiply it by the distance that things are traveling. Or in order to calculate the net velocity, what I would do is take the net rate of movement and multiply it by the distance that things get hopped. That'll give you something that looks like a velocity in the forward direction.